In this video, we're going to talk about capacitors and capacitance. Capacitors are devices that can store electric charges. On the other hand, the capacitance of a capacitor is the measure of its capacity to store charge. Now, the international standard unit is farad, capital letter F. If we have a circuit, for example, we have a circuit. Let's say here is point A. A capacitor is represented with two parallel lines that are of equal length. So let's say this is a cell or a battery, and we have this charge flows like this. This is positive, this is negative. Now this is current that is moving, that is flowing. Current, that's the wire. Now this is the battery. There is a potential difference in this area. This is now point B. Now, the charge flowing through a capacitor is proportional to the potential difference across the terminal. What I mean by that is that Q, the charge, is proportional to the potential difference. If we remove this proportionality sign, we can replace it with a constant called capacitance. So Q is equal to the constant V. So you need to note this. Now, energy that is stored in a capacitor is also known as work done. Energy is given as, let's say, work done, or energy. Let's use U as energy. Now is given as QV. Now the energy stored in a capacitor, you can't get all of them because some part of them are lost to the surrounding in the form of heat, light, radiation, etc. So for a capacitor, work done by a capacitor is half QV. This is the charge, this is the potential difference. You can also say that it is also equal to half CV squared. It is also equal to Q squared over C, over 2C, sorry. Or you say half. So this is the formula for that. Now we have types of capacitors based on symmetry. We have parallel plate capacitor. We have cylindrical plates capacitor, and we also have spherical plates. If we pick the first one, which is the parallel plates, it looks like, let me just have a sketch. They are of equal area, equal sizes, equal area, okay, but opposite charges. So positive charge, negative charge, wire and wire. Now the distance, there is a distance opening here that is filled with what we call dielectric, that does not allow both of them to touch, because when both of them touches, they will discharge each other. It will neutralize, positive and negative, it will neutralize. So we fill it with something like germanium, arsenic, pepper, air. These are examples of dielectrics. Now you need to also understand that the capacitance of a parallel plate capacitor is proportional to the plate area and inversely proportional to the plate distance. What that means is that the more the area of this plate, the more capacitance it will have. But the wider the distance, the lesser the capacitance. So we can write that mathematically and say C is directly proportional to A, but inversely proportional to D, area, distance. So if we remove this, we can say that C is equal to K D, sorry, K, let me write it, sorry. We can say that C is equal to K A over D, which means that C is equal to, instead of writing that K, we use a symbol E naught A over D, permittivity of free space or permittivity of dielectric. So we have either we call it connection or combination of capacitors. Now capacitors are combined so that we can obtain a desired effective capacitance. Two major ways that we can combine them are in series, that's serial connection, then the next one is parallel connection. Now, when they said to be connected in series, let's pick the first one, serial connection. Now, if we have them this way, they are in series. If we have them this way, when the same charge is flowing to them, through them, the same charge flowing through them, they are said to be connected in series. And when they are in series, remember that Q is equal to CV. So the effective capacitance 1 over Q is given by 1 over C1 plus 1 over C2 plus, we can say, to how many capacitors that we have. So you remember the same charge is what all of them experience. So the next one is parallel connection. Parallel connection. Now they are said to be connected in parallel when we have a kind of junction. Then they are in parallel, or they don't experience the same charge. Now, when they are in series, remember, they experience the same and equal charge. But when they are in parallel, voltage is the same. You need to note that. So if we call this C1, call this C2, call this C3, call this C4, for us to get the effective capacitance, that C, or C total, is equal to C1 plus C2 plus how many C's that we have in that circuit. Let's look at this question. It says a 2.4 farad capacitor of area 1 times 10 raised to power 9 meters squared is desired. What should be the gap between the plates of the capacitor? Take permittivity of free space equals 8.85 times 10 raised to power minus 12 farad per meter. Now, from this question, we notice that the capacitance C is 2.4 farad. The area A is 1 times 10 raised to power 9 meters squared. What should be the gap? That is the distance, is what they want us. And E naught is given as 8.85 times 10 raised to power minus 12 farad per meter. From the formula, we have that C is equal to E naught A over D. We are asked to calculate D. We make D subject of the formula. If D is made subject of the formula, D is now equal to E naught A over C. And if we plug in the values, we'll have 8.85 times 10 raised to power minus 12 times the area. The area is 1 times 10 raised to power 9 over the C is 2.4. So if we're to press the calculator, what we're going to have, so this will give you that the distance is 3.7 times 10 raised to power minus 3. So since it's distance in meters, we have another question that says this two capacitors of 2 microfarad and 12 microfarad are connected in series and then connected to an external source of 1100 volts. Okay, so we now say find the total capacitance, the charge on each capacitor, the potential drop across each capacitor. Now, if we can just make a little sketch of this, and external source of 100 volts, this, let's say 6 microfarad, here 12 microfarad, they are in series. So for us to get the total capacitance C total, remember it is 1 over C total equal to 1 over C1 plus 1 over C2. So 1 over C total will be 1 over 6 plus 1 over 12. 1 over 6 plus 1 over 12. Their LCM, which is 12. 6 into 12 is 2. 2 times 1 is 2. Plus 12 into 12 is 1. 1 times 1, 1. So 1 over C total is 3 over 12. 3 over 12. What this thing means is that therefore the C total will invert, which will be 12 over 3, or you say it is 4 microfarad. The second one says we should find the charge on each capacitor. Remember that Q is equal to CV. So this is charge, this is capacitance, or total capacitance, this is the volt. So charge is equal to, remember we got it as 4. So 4 times volts is 100. So we say 100, which will give you 400. 400 charge is measured in coulombs. Now remember that they said for each, that we should get for each capacitor. Now they are connected in series, and if they are in series, they have the same charge. So the Q1 is the same thing as Q2, so they are equal. The other question, third one, said we should get the potential drop across each capacitor. Now we know that Q is equal to CV. If we make C subject of the formula, we're going to have that V will now be equal to Q over C. So for us to get the potential drop for the first capacitor, we can say that V1 is equal to Q1 over C1. So charge is the same, which is 400 divided by the first capacitor happens to be 6 microfarad, which is 6 times 10 raised to power minus 6. So it will give us 6.7 times 10 raised to power 7. So since it's volts, so V2 will be Q2 divided by C2. The same charge is what both of them experience, so 400 divided by the C2 second capacitor is 12 times 10 raised to power minus 6. So if you compute that, you have that V2 is 3.3 times 10 raised to power 7 volts.